Welcome back. Let's focus on a different area in the syllabus, this time a hot favorite to be tested, linear programming. As you know, in the previous exam, linear programming was not tested, to the surprise of so many students and the lecturers too. So there is a very high probability for linear programming to be tested this time. Now, linear programming is all about dealing with constraints, and especially in graphical linear programming, it's about formulating the constraints on a graph, two-dimensional XY graph, to understand the feasible region of operations. Let's look at this simple exercise in the graph, where we have a graph with two demand constraints, demand for X and demand for Y, which is in the Y-axis and the X-axis properly demarcated, and then we have two constraints, material and labor. And all these constraints will form a feasible region, and this is not a difficult task for the students to identify the constraints and the feasible region. And let's assume that we have found the best point, and the best point is now marked on the graph, which is now highlighted to you. Now, it is important for us to understand how to identify effective and ineffective constraints by looking at the graph, because as you know, examination is a race against time and you would not have a lot of time to do calculations. Now, let's see here, the best point is a point where the material and labor constraints intercept with each other, meaning that material and the labor are the effective constraints here. And what does it mean by an effective constraint? That these constraints are utilized to the full. That's why the best point is touching those lines, and they will have shadow prices. And the demand constraints, both X and Y, are ineffective constraints, because you will see the best point is placed well below the constraint lines. So if a best point come and touches the constraint lines, that means those constraints are effective constraints and they will have shadow prices and they are utilized to the full and no slack. Slack means unutilized parts in the constraint. And then if the best point is placed below any particular constraint, it is important to note that they are ineffective constraints. As a result, they will have slack. Now, in this example, you will see demand for X and demand for Y are both not fully utilized. So they are not really constraints. It is important to understand at the exam a very famous examination model of introducing a contract into the learning curve, the linear programming. Now, what happens here is that I think last 2-3 examinations this was tested. Suddenly in the part B or part C, examiner tells you that they have now entered into a contract, and as a result they have to fulfill the contract and then can look into the other normal demand and the production later on. So what students must do first is to calculate the resource requirement for the contract specially, and then take them out from your normal constraint. It is a very standard examination question and a very standard answer to be given as well. I repeat this. What you need to do is calculate the resource requirement for the contract, take it out from the constraints, and recalculate your constraints and redo the graph. Now, example, if we have 2000 hours of labor, you will write your constraints, left hand side the algebra, and the right hand side the value 2000. Now let's say for the contract, if you need 500 hours, the first thing you must do is to take the 500 hours out. So your right hand side will now have 2000 originally available minus 500 left out for the contract. You will have only 1500 hours to work with. And as a result, you will see, if you do this, the amount of available resources will come down because you are leaving something out for the contract. Now let's see the same graph. If we do have a constraint, what happens to the feasible region? Let's look at the slide. The same graph. Now I have taken the taken the requirement for the contract out. The constraint lines are coming down. See, I'm switching between the slides, the previous situation and the current situation. The availability of the resources are coming down. So technically, if there's a contract to adhere to, the feasible region will get smaller. How would you tackle this at the examination? You have to quickly draw another graph, which will not take a lot of time because you are so used to the previous graph, you could easily quickly do it. Now your feasible region is less, and now your best point is also has come down. So with the contract, your best point, both from a x and y point of view, can come down, and you have to recalculate your best point, and to that contribution, so called the best contribution, you will have to add the contribution coming from the contract. And most probably there will be a penalty clause of adhering to the contract and not adhering to the contract. So what you have to do is, if you do adhere to the contract, your best point will come down, and then no penalties would have to be settled because you are fulfilling the contract. And against, another option would be not adhering to the contract. If you do not adhere to the contract, what you have to do, you have to go back to your original best point, no contract, original contribution, but you have to deduct, if there is a penalty, the value of the penalty from the contribution. Another model, maybe to the part B, part C, or to a 10-mark question in part A, would be to test your knowledge on the simplex method. As you know, in the simplex method, no calculations are required. It's a concept to explain the final answer given by the examiner back to the examiner with your ideas. Now let's quickly look at a model of simplex. This could be one of the models you may get at the exam. There are 5 areas to concentrate. Look at the top value, objective function in the slide, 168,700. This is your final contribution by solving the solution. 168,700 is the final final contribution. Now let's look at the value line. You see there's a variable and value. The values are read as 950, 250, 600 and 0. This is your best product mix. We have 1, 2, 3, 4 products, and what is your best mix? 950 of A, 250 of B, 600 of C and nothing of D. Let's look at the third section, which says slack and surplus. This indicates to you what kind of a slack each and every constraint is having. We have 5 constraints: cutting, assembly, finishing, production and a demand constraint. And you'll see 2 constraints, assembly and demand, have slacks. That means they are ineffective variables. 3 constraints, cutting, finishing, production, do not have slacks, meaning they are utilized to the full. They are effective variables. Now concentrate on the bottom right hand corner, says worth or the shadow price. Now see, 3 constraints, cutting, finishing and production, have shadow prices. Quite rightly so, because they are effective effective constraints and they don't have any slacks. And the shadow price for cutting is 9, finishing is 21 and production is 21. So you have to explain these back to the examiner. And quite rightly, assembly and demand, there are no shadow prices because they have not been utilized to the full. There are slack available in the constraint, so therefore they are ineffective constraint. Let's go to the top right hand corner of the sheet. It says relative loss. This could be something new to the students and tested twice in the past papers. Relative loss. Now let's look at product D, a relative loss of 48. What does this mean? This means that if we do move away from the best mix, what is the best mix for product D? Not to produce anything, 0 production. If we decide to produce 1 from product D instead of the suggested mix 0, company will lose 48 pounds or dollars worth of contribution. So what is relative loss? If you decide to go against the best product mix and manufacture one more or one less, this is the amount of contribution you will lose. So it is important in linear programming to keep two things in mind when you get ready for the exam. Number one, how to deal with a contract, allocating resources for the contract and redrawing the graph and recalculating the best point. The second important aspect could be simplex. How do you interpret a simplex final outcome back to the examiner? We'll take a short break to come back and discuss a different topic.